prior to looking at electrochemistry, we want to understand what it means when we say a reaction is an oxidation-reduction reaction. So if you guys remember, we said virtually all reactions can be categorized into three groups. The first group are the acid-base reactions, and we've looked at that in the past. We know acid-base reactions involve proton transfer. So if you look at a balanced equation and you look at two reactants and you see that a proton is being transferred from one to the other, then you know that there is a proton donor, that's the acid, and the substance that accepts that proton is the proton acceptor, that will be the base, and what you end up with is an acid-base reaction. The second class of reactions that we looked at were the precipitation reactions, and we said we use solubility rules to help us. And if you start with two substances that are completely soluble and you combine them and you end up with an insoluble substance, that class of reactions are called the precipitation reactions. And then we said the third class of reactions are the oxidation-reduction reactions, or redox reactions. They mean the same thing, okay? The abbreviated form of the oxidation-reduction reaction is called redox, all right? And these involve electron transfer. So in these reactions, one substance gives off electrons, and the other substance picks up that electron. And we end up by having electrons being transferred. One or more electrons are transferred, and that is an oxidation-reduction reaction. But as all of you can recognize, unlike the previous two where you can look at the reactants, like in proton transfer, you can see that the proton is one substance and then it moves to another. By looking at the balanced equation, it's easy to figure out whether it's an acid-base reaction or a precipitation reaction. In the case of redox reactions, just by looking at a balanced equation, it's hard for us to figure out whether electrons are being transferred because the balanced equation does not have electrons. Is that clear to everybody? So it's very difficult to look at the equation itself and figure out whether one substance is losing electrons and whether the other substance is picking up electrons. So we have to have a system of keeping track of electrons. We call that electron counting or electron bookkeeping. And so if we're going to keep track of electrons, then we have to have an easy system or a set of rules that we apply to assist us in figuring out the number of electrons that are being transferred. And the system that we've come up with is called oxidation numbers. So one way to express the number of electrons lost or gained by a substance in a redox reaction is by assigning an oxidation number to each atom. So this is much like a game. You know, when you play games, you set up rules. And as long as you stick to the rules, everything kind of works out well. It's the same thing here. We're going to come up with a system of rules. And as long as we stick to those rules, then we can figure out whether electrons are being lost or gained, or there's any change in the number of electrons. We're going to look at every atom in a substance individually to figure out whether there's a change in the number of electrons. Okay? So that's what an oxidation number is. An oxidation number is a number, and this number can be 0, positive, or negative, assigned to each atom in any substance in an oxidation-reduction reaction that reflects whether the atom has fewer, and if it has fewer electrons than it started, it has a positive sign. It has more, the oxidation number will have a negative sign, or the same, that will be 0, as the number of electrons as an uncombined neutral atom. So this is so oxidation numbers is just a way for us to keep track of electrons. Okay? And so an oxidation number can be positive, negative, or 0. Okay? And we use Arabic numbers. You know, the Arabic numbers are the 1, 2, 3 that we usually use. So in the online homework, it'll say, give your answer in Arabic numbers, and that means that's what we're using. Later on, you'll see that we can also assign oxidation states, and for that, we use Roman numerals to distinguish between the two. So right now, we're looking at oxidation numbers, and we're going to use Arabic numbers. Okay? So if you look at the class website, I've put the rules up on the class website, and these are the rules for assigning oxidation numbers. Before I start this, usually like solubility rules in Ka value, stuff like that I will provide on the exam. But this I will not give to you because this is something that you need to understand, internalize, and be able to use it intuitively. And so these rules, you need to understand them and be able to apply them, and these rules will not be provided on an exam. Okay? So let's start with the first one. An oxidation number of an element in its natural state is 0. So if you take sodium in its natural state, it's metallic sodium, sodium metal. So it will have 0. If you take metallic silver, that's how the element exists in its natural state, it'll be 0. If you take mercury, the liquid state of the mercury, as all of you know, is the natural state, that will have an oxidation number of 0. Oxygen in its elemental state exists as O2. H2 in its element state exists, hydrogen exists as H2, chlorine exists as Cl2. So as long as it exists in its elemental state, it has an oxidation state of 0. Okay? The second is the oxidation number of a monoatomic ion is the same as its ionic charge. So if it's a cation or an anion, it's monoatomic cation or anion, then its oxidation number corresponds to the charge on it. So Na plus would be +1. Cl minus would be -1. Fe2 plus would be +2. F minus will be -1. So the oxidation number corresponds to the charge. The third is when we deal with oxygen. Okay? In most compounds containing oxygen, the oxidation number of oxygen is -2. So if it's O2, oxygen is the elemental state, it'll be 0. But if oxygen is found in a substance, then the common state is that it has a -2 oxidation number. So if you take magnesium oxide, it has -2. SO2, it has -2. SO3, -2. CO, CO2, any formula where the common form is where it has an oxidation number of -2. The only exception are the peroxides. Now peroxides are pretty rare, all right? And a peroxide is O2 2-. So there are 2 oxygens, and overall it has a 2- charge. So if there are 2 oxygens that have an overall 2- charge, what is the charge on each oxygen? -1, all right? And that's why if you take the exception to the rule are the peroxides in which the oxygenation number has a -1, okay? How do you tell whether it's a peroxide? Look at the formula. If it's like H2O2, or if you have a metal like Na2O2, all right? Look at the charge. If you take Na2O2, you can see there are 2 Na pluses. So that means overall O2 must be 2-. Therefore, each oxygen has to be -1. Okay? But peroxides are not very common. The most common ones you're going to encounter are the ones that have -2. Okay? The fourth rule is that in most compounds containing hydrogen, the oxidation number of hydrogen is +1. So if you take HCl, NH3, H2O, CH4, these all have +1. The exception to this rule are the metal hydrides, in which the hydrogen has an oxidation number of -1. So now if you have like lithium, sodium, potassium, a metal with a hydrogen, then it's a metal hydride. All right, so if you have a metal attached to hydrogen, it would be a metal hydride, and its oxidation number would be -1. Now last is that the sum of the oxidation numbers must be 0 for electrically neutral compounds. For polyatomic ions, the sum of the oxidation numbers must be equal to the charge of the ion. Remember, we're assigning oxidation numbers for every atom in a substance. So if you add up the oxidation numbers, if it's electrical neutral compound like water, has no charge on it, that means when you add up all the oxidation numbers, if you add up the oxidation numbers for the 2 hydrogens and the oxidation number for that 1 oxygen and add them together, it needs to add up to 0. Okay? If it is charged, it needs to correspond to the charge. So if you take chromium, the oxidation number of chromium plus the oxidation number corresponding to 4 oxygens, if you add them up, they have to equal -2. And if you take NH4, if you take nitrogen and add the oxidation number of this to the oxidation number of 4 of these, you should end up with a +1 oxidation state or number. Is that clear to everybody? So now let's apply this. Because we're going to use this often to figure out whether a compound is losing electrons or gaining electrons. So we'll start by taking an example where you're asked to calculate the oxidation number. So we'll start with a simple one. Calculate the oxidation number for carbon in CO2. All right? So your starting point would be to take the compound, and we know that overall this is an electroneutral compound, so the sum of the oxidation numbers corresponding to each of the atoms should add up to 0. So since we need to find the oxidation number for carbon, we're going to call that N, and we have 2 oxygens, so 2 times, what does the rule tell us? What is the oxidation number for oxygen? -2, all right? So this will be -2. So we know the sum of these two should correspond to the overall charge of the molecule. So we know N plus 2 minus 2 should equal 0. Therefore, N equals plus 4. So the oxidation number that corresponds to that carbon will be 4. We always assign oxidation numbers per one atom, all right? So we know that even though there are 2 oxygens there, each oxygen individually has an oxidation number of -2, and because you have 2 of those, we're going to multiply it by 2, okay? So let's take another example like H3PO4. So let's say calculate the oxidation number for phosphorus in H3PO4. So once again, we have H3PO4. The one that we need to figure out, we'll call it N. We have hydrogen and we have oxygen, all right? We have 3 hydrogens, and what does the rule tell us that the oxidation number for hydrogen is? +1, all right? This will be, there are 4 oxygens, and each oxygen we know from the rules will have -2. So that means the sum of all of this should equal the overall charge. So we know that 3 times +1 plus N plus 4 times -2 should equal 0. Therefore, N should equal 8 minus 3, which is +5. All right, so the oxidation number for phosphorus in that compound is +5. Now, after a while, I need you to be able to do this kind of mentally in your head and quickly calculate these. But for now, we'll go through the details. Okay, now let's take the third example. Calculate the oxidation number for chlorine in ClO3 minus. Okay, so once again, if you take this formula, this is what we need to find. So we're going to call that N. You can see that the other component is 3. So we know that each oxygen is -2. There are 3 of those, so that will be -2. But now you can see this is a polyatomic ion that has a charge of -1. So that means the sum of these two should equal -1. So that means N plus 3 times -2 should equal -1. Therefore, N equals 6 minus 1, which is +5. All right? And so, once again, you can see that when you assign oxidation numbers, you have to put signs. It either has to have a negative sign in front if it's a number, a positive sign, or it has to be 0. Okay? Now, lastly, let's take something like thiosulfate, which is S2O3. So, calculate the oxidation number for sulfur in S2O3 2 minus. All right? So now remember, oxidation numbers are always assigned per one atom. So there are 2 sulfurs, so we're going to say 2N. All right? And there are 3 oxygens, and we know from the rule that oxygen has a -2 oxidation number. So the sum of these two should equal 2 minus. All right? So we know 2N plus 3 times -2 should equal -2, which is the overall charge. Therefore, 2N equals 6 minus 2, which is +4. And then we always assign oxidation numbers per individual atom. So each sulfur atom will have +2. Divide that by 2. Each atom has +2. Got it? So for any formula, you should be able to figure out what the oxidation number for all the elements are. Usually, most compounds we deal with have hydrogen on it or oxygen on it, so we use those elements to figure out what the oxidation number for the other one is. If you have cations or anions, you know that they correspond to the charge. Monoatomic and monoatomic cations or monoatomic anions will correspond to the charge as well. Okay? Now let's apply this in an example where we're looking at a redox reaction. So if I take a redox reaction, and we said a redox reaction involves electron transfer. Okay? So let's just take an example where we have two reactants. And let's say in this reaction, A transfers 1 electron to B. All right? So if A transfers 1 electron to B, then what you end up with is A has lost electrons, so it'll be A plus B minus. All right? So you have, so can everybody see that you can't directly see the electrons being transferred. So I'm telling you that 1 electron is being transferred. All right? Now, whenever you look at redox reactions, there's electron transfer, and a convenient way to kind of look at what's going on is to look at what we call half reactions. All right? So if I take half reactions, you can see that A goes to A plus an electron. So in this case, when you write half reactions, you can see that when A goes to A plus, it's losing 1 electron. Okay? Whenever you write balanced equations, remember you have to maintain charge balance. So to begin with, on the A side, everything is electrically neutral. You end up with A plus. So to balance that charge, you can figure out how many electrons you need to balance that charge. So you can see A plus just needs 1 electron to balance that charge, and you know 1 electron has been given up. All right? Now, on the other, so we call this the oxidation half reaction. Remember, why is this the oxidation half reaction? Because oxidation is electron loss. And last time we looked at the definition of oxidation. Oxidation involves the loss of electrons. When a substance loses electrons, we call that oxidation. When a substance picks up electrons, we call that a reduction. So now, oxidation-reduction reactions, we said last time, have to go hand in hand. You can't have one without the other. If something gives off electrons, something has to pick it up. So you need both of those components. All right? So you can't have one substance giving out electrons and those electrons are sitting out there in thin air. All right? You can never have electrons just sitting in thin air. If one is giving it off, another substance needs to take it. And they need to take place at the same time. And so if you look at the reduction half reaction, now this electron that's given off is picked up by B, and it goes to B minus. Once again, charge balance. You have neutral, -1. So on this side I have a -1 charge, therefore on this side I have to have a -1 charge as well. This is called the reduction half reaction. Why? This is where electron gain occurs. All right? Now I want to remind you that even though we write half reactions because they're convenient for us to kind of rationalize what's going on, in reality reactions don't take place in half reactions. Do you understand that? Because the instant the electron is given off, the other is taken up. And so you don't have this process where one electron comes out and the other electron is then picked up. It's immediately transferred from one to the other. So in oxidation-reduction reactions, they just take place instantaneously, and you don't have half reactions occurring. But half reactions is purely a mental process for us to kind of separate it out to understand what is going on. Okay? So if I want to make a little table, I can say that if I take A, so let's look at what happens at A and what happens at B. Remember, we have to look at the reactants. All right? So you can see A loses electrons. In other words, it's losing one electron, one or more electrons. So A loses electrons, B gains electrons. All right? A undergoes oxidation, or it is oxidized. And we say B undergoes reduction, or it is reduced. All right? Now, last time we looked at, when you look at redox reactions, you need to be able to identify what is undergoing oxidation or what is being oxidized, what is undergoing reduction, what is being reduced. All right? The next is that you need to know which is the agent. All right? So since this is undergoing oxidation, this is the, A is the reducing agent. This is the agent that's responsible for reducing this substance which is undergoing a reduction. And B is a oxidizing agent. All right? Whenever a substance undergoes oxidation, the oxidation number increases. So the oxidation number of A increases. All right? So the oxidation number of A increases. And if it's undergoing a reduction, the oxidation number of B decreases. So these are important points to remember. If you're looking at an oxidation-reduction reaction, I need you to be able to look at each one of these and be able to identify for each reactant. You need to know which one is losing electrons. You need to figure out which is gaining electrons. You need to figure out which one is being oxidized, which is being reduced. You need to figure out which is the oxidizing agent, which is the reducing agent. Whenever you have an oxidation, the oxidation number increases. All right? When a substance loses electrons, its oxidation number increases. When a substance gains electrons, its oxidation number decreases. So in an oxidation-reduction reaction, if the oxidation number changes, you know that it's oxidation-reduction reaction. One substance oxidation number will go up. That means it's oxidized. And another substance oxidation number will decrease. That's the one that's being reduced. Okay, so let's take an example. And we'll start with some simple examples, and then we'll go to more complicated ones. So let's take some examples. And the first example I'm going to take is where you have potassium solid. And so this is metallic potassium reacting with chlorine gas to give you an ionic compound, which is potassium chloride. Okay? So quickly check whether this equation is balanced. You have two potassiums, you have two chlorines. Okay? Now, for you to figure out whether it's a redox reaction or not, we have to look at oxidation numbers. Okay? So to begin with, we always look at it per one atom. All right? So in this, there are two potassiums in this balanced equation. And so if I take potassium, this is an element in its natural state. Therefore, its oxidation number has to be 0. And there are two coefficients. I'm going to put the coefficients outside. Okay? Over here, chlorine is, there are two chlorine atoms, but this is an element in its natural state. Therefore, the oxidation state of the two chlorine atoms in Cl2, each one will have an oxidation number of 0. Okay? So there'll be 2 times 0. Now, on this side, we end up with an ionic compound. All right? This is a metal, non-metal combination. If it's an ionic compound, we have to have a cation and an anion. So if I take the potassium, you can see that that's K+. Therefore, each potassium will have a +1, and each chlorine will have a -1. So what's outside is the coefficients in the balanced equation, or the number of atoms that's there in the balanced equation. Okay? So now we have to look at this equation, and we want to figure out, does the oxidation numbers change? So if you look at potassium, each potassium atom goes from 0 to +1. So is there a change? Yes. Now you ask yourself, so that's got to be a redox reaction. Secondly, is the oxidation number increasing or decreasing? So if you take potassium, it goes from 0 to +1, so it increases. Remember, if the oxidation number increases, what is that? Oxidation. All right? So we start looking at the two reactants, and we're going to say that when this goes to that, oxidation number increases. And we know that's an oxidation. And by how much does it change? Each one goes from 0 to -1. So that means that if there's a change by 1, all right, it goes from 0 to +1 rather. If there's a change of 1, that means 1 electron is being transferred. But there are 2 atoms, so overall you can see 2 electrons are being transferred. So overall, 2 electrons are transferred. As each potassium atom goes from an oxidation number of 0 to +1, there's a net change of 1. The net change of 1 means that 1 electron is being lost. But overall we have 2, so you multiply it by 2. And so in this reaction, 2 electrons are being lost. All right? Now, if you go to what's being reduced over here, now your chlorine, if you look at the oxidation number, goes from 0 to -1. So you know that oxidation number decreases. And if it decreases, it means it's a reduction. And if you take each chlorine atom, it changes by 1. Okay? So since electrons are being lost, I'm going to put a negative sign here to show me that electrons are being lost. All right? A negative sign means electrons are lost. Positive signs mean electrons are being gained. So if you look at this, each chlorine atom goes from 0 to -1. So it's a net change of 1. So it decreases by 1. So I'm going to say 1 electron. But since there are 2 atoms involved, altogether 2 electrons are being lost. Okay? So we've figured out from this, by looking at oxidation numbers, that 2 electrons are lost and 2 electrons are gained. All right? Now the cardinal rule is that the number of electrons given off have to equal the number of electrons taken up. If that doesn't work out, then you know there's something wrong with your rationale. Do you understand that? Because you can't have 10 electrons given off and only 5 taken up. All right? The number of electrons given off always have to equal the number of electrons taken up. All right? And you can see 2 electrons are given off, 2 electrons are picked up. Now, so what is undergoing oxidation? Potassium, this is oxidized. You can see chlorine is reduced. All right? So the substance being oxidized is potassium because it's undergoing oxidation. The substance being reduced is chlorine because its oxidation number goes down. So that's the substance being reduced. If this is being oxidized, this is the reducing agent. And this is the oxidizing agent. And we know overall 2 electrons are transferred. All right, so it's very, very important that every example that you look at, you have to be able to go through this process. You've got to figure out what's being oxidized, what's being reduced, how many electrons are being transferred, and you make use of oxidation numbers to do that. Okay? So let's take another example. So we're going to look at the combustion of methane. So what happens if you burn methane in oxygen? Now a combustion reaction is also an oxidation-reduction reaction. Remember? So if I take methane plus 2O2 gas, giving me carbon dioxide plus 2. Okay, so we're looking at the combustion of methane. Make sure the equation is balanced. You can see there's 1 carbon, 4 hydrogens, 4 hydrogens, 4 oxygens, 2 plus 2, 4 oxygens. Okay? So I'm going to tell you ahead of time that this is a redox reaction. Okay? So if you take a redox reaction now, you've got to figure out what's being oxidized, what's being reduced, how many electrons are being transferred. Okay? So for carbon, by now you should be able to do this really fast. The hydrogens each have +1. There are 4 hydrogens with +1. So what's the oxidation number of carbon? -4. Okay? If you take hydrogen, there are 4 times +1. So that will be the oxidation number assigned to each of the hydrogens. Each oxygen, can you see that there are 2 oxygens here times 2? There are 4 oxygens. It's an element in its natural state. Each oxygen atom will be 0. Okay? Now let's turn to this carbon. To figure out what the oxidation state of this carbon is, we turn to oxygen. Remember, each oxygen atom has, what is the oxidation number? -2. So there's -2 times 2 gives me -4. So if oxygen is -4, the whole compound is electrically neutral. What is the oxidation number of carbon over here? +4. Okay? And we know there are 2 oxygens. That's going to be -2. Now over here we have hydrogen. Each hydrogen is +1. How many hydrogens do I have? 2 times 2, 4. And then if I take the oxygen, there are 2 oxygens, and I know that's -2. Can everybody see I've assigned oxidation numbers for all of the atoms? Now I look at one atom at a time and figure out which ones are undergoing changes. So we start with carbon. Carbon starts from -4 to +4. All right? So that's 1. Now, does hydrogen change? The hydrogen atoms here are +1. The hydrogen atoms here are +1. So hydrogen does not change. Let's look at oxygen. Oxygen goes from 0 to -2 over here and -2 over there. Do you see that? So that means oxygen is changing, and it's changing. Both sets of oxygens are undergoing a change. Okay? So let's start with carbon. Now look at the oxidation number for carbon. Does that increase or decrease? It increases. It goes from -4 to +4. So since the oxidation number increases, what do I know? This is the oxidation, and methane is being oxidized. All right? Now look at by how many does it change? Remember, there's 1 carbon atom at the beginning, there's 1 carbon at the end. So if I go from -4 to +4, what is the change? 8. So that means there are 8 electrons involved. All right? And so this is oxidation. Electrons are being lost. So we know that there are 8 electrons involved. So overall, 8 electrons are being transferred. Okay? Now let's go to the oxygen side. It goes from 0 to -2. Does the oxidation number increase or decrease? It decreases. Remember, if the oxidation number decreases, we call that process reduction. Okay? Now let's look at how many oxygen atoms there are. There is 2 times 2, 4 oxygen atoms. There's 2 plus 2, 4 oxygen atoms. So there are 4 oxygen atoms. And each oxygen atom goes from 0 to -2. So what is the change? 2 electrons. If it's a reduction, are electrons picked up or electrons lost? Picked up. So you know that they're times +2, which gives me +8 electrons. So how many electrons are being transferred here? 8 electrons. So in this oxidation-reduction reactions, you can see that the substance that's undergoing oxidation is methane. So that's being oxidized. The substance being reduced over here is oxygen. All right? So if this is being oxidized, this would be the reducing agent. If this is being reduced, that will be the oxidizing agent. And how many electrons are transferred? 8 electrons are transferred. Okay? I need you guys to be able to do this in your sleep. Okay? Because if you can't figure out how many electrons are being transferred, then the whole exercise is a waste of time. Do you get it? So, and later on when we're going to look at electrochemistry, I need you to be able to just look at a reaction, figure it out, and know how many electrons are being transferred. Okay? Now let's take another example where let's say I have SiCl4 plus let's say that's liquid plus 2H2O liquid gives me 4HCl aqueous plus SiO2 solid. Okay, so once again, let's take a look at this. So now we can go pretty fast. There are 4 chlorines. Each chlorine has -1. So what is the oxidation state of silicon? +4. There are 4 chlorides, and each one is -1 because remember chlorine, Cl- has a -1 oxidation number. Here there are 4 hydrogens. Each hydrogen is +1. There are 2 oxygens. Each oxygen will be -2. All right? Now on the product side, we have 4 hydrogens, so it will be 4 times +1. There are 4 chlorides, 4 times -1. If I take the silicon over here, you can see it's +4. This is 2 times -2. Now I'm starting to move pretty fast because that's sort of the pace at which you need to be able to analyze these reactions. Okay? Now look at this and tell me, is anything undergoing any change? Let's start with silicon. Silicon is +4. The oxidation number is +4. At the end of the reaction, it's +4. Does that change? No. Let's look at chlorine. Each chlorine atom to begin with is -1. On the product side, each chlorine is -1. Does that change? No. Now let's turn to water. Each hydrogen is +1. On the product side, the hydrogen is +1. If I turn to oxygen, each oxygen is -2. On the product side, each oxygen is -2. So do oxidation numbers change here? No, there are no changes. So is this a redox reaction? No. Okay, there's no electron transfer. All right, so what kind of reaction is this? Remember, it has to be either acid-base, precipitation, or oxidation-reduction reaction. Look at the hydrogen atom. Do you see hydrogen atoms moving from one to the other? Where does hydrogen start with water? Is the hydrogen moving away from water? Is it staying together with water? So can you see there's a proton transfer? There are proton transfers taking place. If it's a proton transfer, what kind of reaction is that? Acid-base. Okay? So this is not a redox reaction. So not every reaction that you look at has to be redox. And the way to figure it out is to look for oxidation numbers and whether there's a change. Okay? So now we're going to look at something that's very, very important, and that is balancing oxidation reduction reactions. All right? Now, up to this point, so I'm going to give you one example. So let's take an example. And let's say you want to balance the equation copper plus HNO3 giving you copper nitrate plus nitrogen plus H2O. Now it turns out that up to this point, if you want to balance a chemical equation, all right, you've only looked at trying to balance atoms, all right, and you're pretty well versed at balancing equations. But it turns out that there is a class of oxidation-reduction reactions that are virtually impossible to balance. All right? And this is one such example. So if you wanted to use sort of the general form that you've used in the past, remember, usually we say when you balance equations, the number of atoms at the beginning should equal the number of atoms at the end. And you just play around with this, and there's no hard and fast rule on how to balance it. It turns out if you try to balance this equation, you can work on it for a month, and unless you follow a general strategy, you will not be able to balance this equation. All right? And so these are challenging equations to balance, and the reason is that you have, these are redox reactions, and in redox reactions, when you balance redox reactions, the underlying principle that you want to remember is the number of electrons given off have to equal the number of electrons taken up. Okay, so that's going to be underlying principle. So if you want to balance this equation, I'm going to write them out so that it's in one line, because so we have HNO3 giving you copper nitrate plus NO2 plus H2O. The first step is we're going to assign oxidation numbers. Okay, you have to, in order to balance this equation, you have to assign oxidation numbers. So I'm going to do this fast. This will be 0. Each hydrogen is +1. Each oxygen will be 3 times -2. All right, so can you do this? This will be 6. This will be +1. So what should nitrogen come out to be? +5. Each copper, this is copper 2+, because there are 2 nitrates. So you know that the oxidation number of copper is +2, and therefore you can see the charge is +2, oxidation number is 2. Each nitrogen, there are 2 nitrogens, each nitrogen will be +5. Each oxygen, there are 6 oxygens, will be -2. Now over here I have 1 nitrogen. What is the oxidation number for that nitrogen? +4, because there are 2 oxygens over here. Am I going too fast? I need you to work at this pace, okay? So people who complain that they don't have time on the exam have not mastered this skill or haven't practiced enough to be able to do it kind of intuitively, okay? So water is, there are 2 hydrogens, each hydrogen is +1, and then does everybody agree with me? So what I've done is I've just assigned oxidation numbers for all the elements, okay? Now my next step is to figure out which ones are undergoing changes. All right, so what is the first one that undergoes a change? Copper. All right, what else changes? Nitrogen. But can you see that the nitrogen is kind of tricky, because some of the nitrogens don't change and some of them do change. Do you see that? This is why this equation is so hard to balance. Because can you see there are NO3, some of the NO3s, remember NO3, the nitrogen here has a +5 oxidation state. Some of them remain +5, and some of them go to +4, all right? And therefore, we need to figure out how many of these actually change and how many of those nitrogens don't change at all, okay? So remember, what is the underlying principle? The number of electrons transferred has to be the same. So the number of electrons given off has to be the same as the number of electrons taken up. So now let's turn to this. If you take each copper goes from 0 to +2. Is the oxidation number increasing or decreasing? Increasing. If it increases, what do we know? It's an oxidation. And each copper atom changes from 0 to +2, therefore 2 electrons are lost. All right? So if 2 electrons are lost, how many electrons need to be taken up? So we know here it goes from +5 to +4. Do you see that? So that means this is the reduction. And we know that each nitrogen goes from +5 to +4. So that decreases. That's why it's a reduction. By how much does it change? By 1. So I know that each nitrogen is picking up 1 electron, but if I want to make these equal to each other, I have to multiply it by 2 so that 2 electrons are picked up. All right? So that means that I have to have 2 nitrogens here. Do you see that? Because 2 of these are the ones that are being reduced. Okay? So now let's go back to this equation. I have copper, 1 copper, 1 copper. So I can't change that now, because if I double this by 2, then 4 electrons will be given up. So I'm going to stick to 2 electrons being given off. I can't change that. Okay? Now I have 2 NO2s that do change. But remember, there are 2 NO3s. There are 2 nitrogens here that don't change. So what is the number I need to put here? Can you see I need to put 4 there, because I put 2 here to balance the 2 electrons. So I have 2 nitrogen sources here, plus there are 2 here. So this 2 plus this 2 gives me 4 nitrogens on this side. So I have 2 nitrogen atoms coming from here, 2 nitrogen atoms coming from here. Overall, I should have 4 nitrogen atoms on this side. Did you get that? Once you get that, your equation is balanced. Otherwise, if you're just trying to do atom balance, you'll be sitting there for days and you will not be able to figure it out. If you do, it's purely by chance. All right? It's just pure luck that you got it. Okay? So once you figure that out, now I can go back and say, so I have 4 hydrogens, therefore I need 2 waters on this side. Okay? Now let's make sure our equation is balanced. All right? And I'm going to now confirm. I have 1 copper, 1 copper. I have 4 hydrogens. I have 2 times 2, 4 hydrogens. Now let's go to oxygens, nitrogens. I have 4 nitrogens here. So I have 4 nitrogens here. I have 2 nitrogens and 2 here, 4 nitrogens. Now let me do the math for oxygens. 4 times 3 gives me 12 oxygens. All right? So here I have 2 times 3 gives me 6, plus 4, 10, plus 2, 12. So I know all my oxygens are balanced. And I know now I balanced the equation. Did you guys get that? And so this way, you can balance the equation by looking at oxidation numbers. Okay? For discussion next week, I will give you lots of examples to practice. Now, within the last 3 minutes, I'm going to do another example, and so we still have 3 minutes. So if this is my balanced equation, NaCl plus H2SO4 plus MnO2 giving me Mn2SO4 plus MnCl2 plus H2O plus Cl2. Okay, now this question comes directly from an exam that I gave 2 years ago. All right? So I'm just pulling an old exam question, and you're asked to balance this equation. All right? If you were to try to balance this equation by sort of the methods that you've used before, which is just looking at atom balance, you would not be able to balance this equation. All right? So it's a redox reaction. I have to balance this equation by looking at the number of electrons given off and the number of electrons taken up. So quickly, I'm going to assign oxidation numbers. +1, -1. 2 times +1. This will be -2 times 4. So remember, this is 8 minus, 2 plus, so this has to be +6. All right? Now, look at manganese. It's a transition metal, so we've got to rely on oxygen. Oxygen is 2 times -2, therefore each manganese will be +4. On this side, I have 2 manganese, so it'll be 2 times. Now, the sulfate is SO4. Oh, wait, my formula is wrong. What did I write? Na2, oh, this should be Na2, sorry. All right, there's no charge balance there, so, and I copied this wrong. Okay, so there are 2 sodiums, each one is +1. Each oxygen is -2 times 2. Each sulfur will be +6. Over here, each chloride is 2 times -1, so this will be +2. This will be +1 times 2, -2, 0. Over here? Over here. Yes, thank you. All right? Now, I need to figure out what is undergoing changes. All right? Sodium is +1, sodium is +1, so sodium didn't change. Okay? Chloride is -1, it goes to 0. So we know chlorine has changed, but there are 2 types of chlorine. There are some chlorines that don't change and some that do. All right? And then the other thing that changes is manganese goes from +4 to +2. All right? So let's start with manganese. It goes from +4 to +2. Is that an oxidation or is that reduction? Increases or decreases? So if it decreases, it's a reduction. Okay? How many electrons are being, if it's a reduction, it gains electrons. It goes from +4 to +2. 2 electrons are picked up. Now let's look at chlorine. Each chlorine goes from -1 to 0, so it's increasing. So that means that's an oxidation. And it increases by 1, so that means that 1 electron is being picked up, or lost, I'm sorry. 1 electron is being lost, Now to balance this, I need 2. So I'm going to multiply that by 2. So that means I need 2 chlorines on this side. So if I have 2 chlorines on this side, 2 that undergo change, but there's 2 that don't change. So how many do I put here? 4. All right? Because there are 2 chlorines that go from -1 to 0, and there are 2 chlorines that go from -1 to -1. All right? So I need 4 NaCl. Once I have got that, now I need 4 sodiums, so I'm going to put 2 sodiums there. Now if you look at this sulfate, I have 2 entities of the sulfate, so I need 2 sulfates over here. Now I have 4 hydrogens, so I need 4 hydrogens over here, and now my equation is balanced. I will repeat this example. I want you to take a look at this example at home and think about it. I will repeat this example at the beginning of class next time and go through this once again, because it's very, very important that you understand how to balance redox reactions, okay?